So let's start getting into measure theory by having a fairly well-defined project, the thing that we're trying to understand. Now, we would like to be able to talk about measuring sets of real numbers in a way that is consistent with the notion of the length of, let's just pick arbitrarily, an open-bounded interval. We could have picked a closed-bounded interval or several other possibilities, but somewhat arbitrarily, I'm just going to choose to take our canonical thing that we understand to be the length of an open bounded interval. And we're not going to talk about right, at least not for a while, we're not going to talk about the length or the measure or whatever of a closed-bounded interval, because I want that to kind of come out of our minimal conversation about these open-bounded intervals. So anyway, point is, this is perfectly well understood and there is no mystery here. Now, let's think about other sets that are not intervals, like, for instance, the union of the interval from 0 to 1, together with the interval from 2 to 3. Now, we wouldn't want to talk about the length of that because, in a sense, like, length just feels like the wrong word. It's this broken up object, so you wouldn't really want to call that the length. So we don't really define length for things that aren't intervals. Rather, we would instead call it the measure. And in particular, when I write this M, what I mean is the length measure, because we will see much later on that there are many versions of measure, but just for our starting example, I want to talk about the, so to speak, length measure, which is to say I'm measuring sets of real numbers. They may not all be intervals, but we want to do this in a way that is consistent with the notion of the length of an interval. And so what I mean by that is that, like, if you have this disjoint union of two things, and this has length 1 and this has length 1, then we would want to define this measure to be, the measure of this or the length of this plus the length of that, so come out equal to 2 in this example. Notice that disjointness was an essential requirement here, because if you took the interval from 0 to 2 and 1 to 3, then if you didn't care about disjointness, or if you weren't careful, then you would say that that's 2 plus 2 is 4, but you would also say that that is the measure of 0 to 3, and as an interval, we know perfectly well that that should come out equal to 3. So you do need to, right, in order to not get an inconsistent concept here, you want to not do this to overlapping sets. But even though some of those examples are easy to understand, and you might even convince yourself of what to say about certain other examples like closed bounded intervals or infinite intervals or whatever, some sets, like the set of all rational numbers, are a lot harder to come up with an argument for if you don't have a rigorous theory about what is going to define this M. So you could propose that it should be infinity because this thing extends out to negative and positive infinity. It's dense in the real numbers. So you could convince yourself through arguments like that this should have infinite measure. You could also convince yourself, well, it's countable. I mean, these intervals are uncountably infinite. This is only countably infinite, so maybe it should be 0. Or maybe there's some reason where it, or certain subsets of it, should be like a positive real number. Who knows, right? Until we get rigorous about what M is defined to be, then we don't have a very, universally convincing answer about what this ought to be. But Q is not even the weirdest set of real numbers that you could use to make this point. Now, the Cantor set is, in fact, you may have seen it in an earlier class, or you may not have. We'll talk more about it later on. But The important arguments that would surround this is the fact that it is an uncountably infinite set and therefore has the same cardinality as these intervals, and yet it also contains no intervals, right? And so if it's uncountably infinite, maybe you think it should have measure some finite positive number, positive real number, or maybe because it has no intervals, you think that it must have measure 0, perhaps. Again, this is a weird set, and if we don't have principles guiding us on how we make these decisions, then we could end up having inconsistent decisions and who knows what. So the project is to define M such that it is consistent with L, right? That is to say, M on an open interval, open bounded interval, will give that interval length. And then whatever we are committed to for that, for general sets of real numbers, we just accept that as our definition of what the measure of a set of real numbers is. So that's the project, defining M.